Right, with that, we'll get started. Let's go and open the Google Earth Engine code editor. This is the URL to open the code editor. You can open a new browser tab and go to code.earthengine.google.com. If you are in India, there's a special URL, code.earthengine.google.co.in. This has the Earth Engine version, which is compliant with the Indian laws. So if you are in India and using Earth Engine, make sure you use the .co.in version. For everybody else, it's .com. So depending on where you are, you can go to any of this URL and load the code editor. I'm going to go and open the code editor. We have shared a link to add the course material repository to your code editor. If you find that link and click on it, you should have this repository called end-to-end GE in your code editor. For you, it will be under the Readers tab. Since it's my repository, for me, it appears in the Owners tab. But go and find this end-to-end GE repository in your Readers tab. It should have this 5 modules and the code for this. Go and open this 01 Earth Engine Basics folder. Inside it, there are a bunch of scripts. Let's open this first script, Hello World. You can see the structure of the repository. All the sections have 3 scripts, A, B, and C. We start the explanation with the A script. I'll type some code. I'll explain what I'm doing. You'll learn some new concept. Everything that I'm typing is already there in the B script. So you don't need to take any notes or type code because it's already there. So we'll start with the A script. I'll slowly explain and build the full script, which is already there in the B section. And then we'll have a C section, which is an exercise. Right? So when I'm explaining the script, you can pay attention here, learn the concept. The full script is already there, accessible to you, so you can refer to that later on. And then we'll come to the C script, which is the exercise. And you can see the entire course is structured like this. So we'll spend a few minutes learning about new concept, do the exercise, and then move on to the next concept. All right, let's start the first script. We call it Hello World. When you're learning a new programming language, new system, it's useful to just learn how to print Hello World. In Earth Engine, in JavaScript, it's very simple. You can use the print function. This is the Earth Engine API function, which takes an input and prints it. When I click run here, you can see it prints Hello World on console. So this is the place where any text output that you ask Earth Engine to produce will be printed. If you ask Earth Engine, give me the total forest loss in hectares. And if you print it, it'll be printed here. So any text output will be printed here. This place also can hold charts and other elements. So if you ask Earth Engine to create a chart, it'll be printed here. The print function can take any input. I can change the input and say, hello class. And when I run again, you can see the output changes. So the print function takes some input, prints it on the console. You can use single quotes or double quotes. Anything you put in single or double quotes in Earth Engine is recognized as a text. And Earth Engine supports both. JavaScript doesn't matter if you use single quotes or double quotes. It's purely a matter of preference. My only advice is if you use single quotes everywhere. If you use double quotes everywhere. So here we have some text that we have quoted. If you make a mistake in your code, so for example, I wrote a code like this, and the code has some error. You'll see this red button. The code editor will give a warning saying that, okay, there's some problem. You try to fix the problem. And once you fix the problem, the error will go away. And then you'll be able to run the code. Let's learn some of the basic fundamentals of JavaScript. You'll only need to learn JavaScript that is enough to call the Earth Engine API functions. When you use Earth Engine, you have to define some variables. You need to write some functions and call the Earth Engine API. So we'll learn just the basics of JavaScript that will allow you to work with Earth Engine comfortably. When you write some code, you can see it in JavaScript, you end each code statement with a semicolon. That indicates that my statement is complete. If you forget a semicolon, you'll get this warning here, missing semicolon. JavaScript is again very forgiving. It says, I don't care if you missed a semicolon, I'll figure out that you missed a semicolon. Your code will still run. It will not stop, but it's a good practice to add a semicolon. So, and again, I don't like seeing all these warnings in my code, so I'm very particular about adding a semicolon. But again, if you forget it, doesn't matter. If you start any line of code with 2 forward slashes, that is known as a comment. This statement, which is starting with 2 forward slashes, will not get executed. When I run this, nothing happens because this part will be just ignored by the system. This is useful to add some comments and helpful documentation for your code. It's also helpful to stop a certain part of the code from running. So let's say I don't want to run this code, I can just prefix with 2 forward slashes and the code won't run. So if you have some block of code and say, I only want to run this part, you can comment out the rest of it. As you are writing Earth Engine code in this code editor environment, you can learn about some shortcuts. One shortcut that I use all the time is Control plus Enter. This is a shortcut to run the script. So instead of you going and running this, clicking the button, if you get used to this Control plus Enter shortcut, you'll be able to run the code automatically. So I can change this back to world and Control Enter, and you can see it ran. I don't have to reach out for this. It's a small thing, but really helps you on this. Another shortcut is Control plus forward slash, which is for commenting. So if I go in a line and Control plus forward slash on Windows or Command plus forward slash on Mac. This is for commenting. So if I go and say Command forward slash, it'll comment. And again, if I do Command forward slash, it'll uncomment. This also is useful for bulk commenting. I select multiple lines and do this, it'll remove and add comments. So very useful if you want to say, I don't want to run this block of code selected, and you can comment it out. Some of the building blocks of the programming language, the JavaScript language, is first thing we need to learn is something called variables. In JavaScript, if you are defining any value, you need to prefix that with a keyword called var. So let's say I have this variable called city. I'm assigning this with a value called Bangalore. A variable is something that can hold a value and it can reproduce this value at later on. So if I say print city, what do you think it'll print? If I run the script, what do you think will be the output printed in my console? Because when you ask JavaScript, what is the variable, it'll print the value that is stored in the variable. What about this? Something in quotes. A quotation mark says this is the text. So it has to reproduce it exactly. This is one of the common mistakes that beginners will make, that you'll say, I want to print the variable city, but then you'll put in quotes and you'll get city, not the value that is contained in the city. So make sure if you put something in quotes, it's a text. Something that is not in quotes has to be a variable that has already been defined. In JavaScript, you can just add variable and assign some number value as well. So you can assign some numeric value and print it the same way. You don't have to declare the types of the variable. You can just assign a number or a text and JavaScript will interpret it correctly. Next thing you need to learn is how to create list. Many times you want to store not just one value, but a set of values. Let's say you want to do some analysis for all the cities in a country, and you want to store them as a list. So in JavaScript, you need to use square brackets for creating a list. Let's create this list called major cities. We'll say I have this 4 cities, which are the metro cities in India, and I can create a list with the square brackets and comma separated values. So I have this list of 4 things, and let me print it so you can see what difference does it make. You can see now when I print major cities variable, it says I have these 4 values. If I expand this triangle is called a zippy. If I expand this zippy, you can see it contains 4 things inside of this. So I've created a variable that contains 4 things. Anybody know what is this 0, 1, 2, 3? What is it called? And why there is 0, 1, 2, 3? It's called an index. An index is the position of the item in a list. In JavaScript and Python both, the indexing starts from 0. So our programmers will have to unlearn your stuff. In our indexing starts from 1. In JavaScript and Python, indexing starts from 0. So if you say I want the 5th item, you'll have to say index number 4. And that's even Earth Engine API, indexing starts from 0. Also, you saw that I defined my variable in a funny way. This kind of variable naming is called camel case. Camel case is the preferred method for JavaScript variables, where you start your variable names with a small case and capitalize every word. So if I wanted a variable called major cities in India, I would write it like this. Right? You capitalize every word. And this is kind of a preferred method Even the Earth Engine API, if you see any of the API functions, you'll see all of the API functions follow the same method. So the API functions will also follow camel case. So if you use camel case in your code will be consistent. In Python, the preference is to use underscores between the words. You can use either, doesn't matter. It's just a kind of convention. So I prefer when I'm writing Earth Engine code, I stick to the camel case convention. So my code is consistent with the Earth Engine API. One of the other things that you may have to use when calling Earth Engine function is something called a dictionary. When you put something in a list, there's no way to recall the value. You can only recall them by the number. So you have to remember, oh, I put this item as a third thing. I put this in the fourth thing. If you have structured data and you want to kind of name each item, you can use a dictionary. A dictionary uses something called curly brackets. So let's say I want to define a dictionary called city data. I can use curly brackets, and for each item, I can name the item. So I can say I have a key called city, and the value of this is the name of the city. I have another key called population, and the value of this is some number. And then I have another key called elevation, and its value is this. So now I have 3 items I've stored, but I've named each of them. Let me print this and see. You will see the difference between a list and a dictionary. You can see now when I expand this, it doesn't have 0, 1, 2, 3. Each item has a name. So if I wanted to know what is the elevation, I can just say, give me the elevation from this variable city data. So dictionaries are useful for storing structured data. In Earth Engine, you'll use dictionaries for calling functions. You'll also use it to store things like metadata and a lot of structured data that you'll use in your program. JavaScript allows you to break your command into multiple lines. So if you have a long command like this, you can break it down over multiple lines. Just makes it easy to read. So you'll see people defining dictionaries like this. Same thing, doesn't matter, but again, your code is much more readable if you break it down over multiple lines. So we learned about variables, we learned about lists, dictionaries. We just need to learn one more thing to use JavaScript with the Earth Engine API, and that is the concept of functions. A function is something that takes an input, processes the input, and gives you an output. A lot of your coding in Earth Engine is taking your remote sensing workflow and writing a function to implement that in a function. So you say, I have an image, I want to detect water. You write a function that takes an input as an image, do your work, and detect water, and return that. Now, once you have a function, you can run this function on all images. And Earth Engine allows you to run this in parallel across many machines. So most of the time, what you're doing in Earth Engine is encapsulating your workflow in a function, so you can run it on all images, all features, over multiple years. So we'll have to learn how to write a function. Earth Engine has API functions called built-in functions like print, but you can write your custom functions. To write a custom function, you need to use the keyword called function. Let's write a function. So I have a function. I'm calling this function as the name greet. You can define this using the function keyword. A function can take some inputs and does something and returns the output. So this is the structure of a function where you say, this is a function using the function keyword. It takes some inputs, takes that inputs, processes that, and returns an output. You can call this anything. You can say this function gets one input called x, and I can do something with x and return something. So let's say I will say my greeting is hello plus x, and I can return greeting. So this is a simple function. Let's test this function to see if it works. I can say greet word. When I run this function, it says, okay, there's a function called greet. Whatever input I've given will be assigned to this variable x, and will be used inside the function, and then it'll return that. Let's see what does it return. Let me print the output here. It prints hello world. The good thing about function is it allows you to write code and not repeat yourself. So I can give a different input. I can say greet class, and I'll get hello class. I didn't have to write the code for this. I just change the input. The input gets processed through the function, and I get an output. What about now? What do you think will happen when I run the code? I have a function, it says function of x, var greeting, hello plus x. What do you think will happen when I run this? Okay, when I run this, it says undefined. So I don't know. The function didn't return anything. It's null. This is a very common thing. Many of you will say, I've implemented this function, I'm running this, I'm not getting an output, or I'm getting an error. The reason is you may have forgotten to return the output. So make sure you always have a return statement. A function must return something, and then that'll be used as an output. The variable here doesn't matter. You can have anything. I can just say name and hello plus name. This is just a variable name. So whatever you give input to the function will be stored in this variable called name, and this name can be used inside the function to access the input. So it could be X, Y, whatever you can assign that. And that's it. That's all the JavaScript you need to learn to use Earth Engine. I'm serious. I don't know any more JavaScript. If you ask me how to do anything more in JavaScript, I don't know. And I've been using Earth Engine for 7 years. So again, this is all the JavaScript you need to know to use Earth Engine. Anything more, even stuff like how do I add two numbers? I've not taught you how to add two numbers. How will you write a program? Well, you use this using the Earth Engine API. So for everything else, you will need to use the Earth Engine API. You just need to know how to define a variable, how to define a list, how to define a dictionary, how to write a function, and how to use commands and some shortcuts. That's it. Once you know this, you'll be able to write Earth Engine API code and do your remote sensing work. The rest of the course is learning how to do your work using the Earth Engine API. Okay, let's write one more function. Let's say I have a function called add numbers. This function can take two numbers, X and Y, and I want to, get the sum of it. So I'll say X plus Y, and I'll return the sum. So this is a function that takes two numbers and adds them up together. So now I can call this function add numbers 2 and 3. And now if I print this, it'll give 5, because this 2 will be assigned to X, 3 will be assigned to Y, and they'll be added here, and I'll return the sum. And why a function? Because now I can call this number with any two numbers, and I get the answer. So if I said add numbers 20 and 30, I get 50. So a function can take some inputs, use those inputs to do some processing, and return an output. And now you can call the function with different inputs, and those will be used by the function to do some processing, and you get a different output. In the context of image processing, most of the function will take some image as an input. And let's say I want to compute NDVI for some images. I have 1,000 images, so I'll just write a function that'll take one image, compute NDVI, and return that NDVI image. And now I can run this function on all of those 1,000 images, so that for each image, it'll compute NDVI. All right, let's do an exercise to capture your knowledge. Before that, if you have typed some code and you go and try to save this, the first time you try to save this, it'll say, you cannot save this. This is a read-only repository, because this is my repository, it's my script. I have not given you write access. You only have read access. So when you try to save it, it says, oh, do you want to save it in your own repository? So I say, okay, I'll make a copy and save it to my own repository. If it's the first time that you are doing this, you'll be asked to choose an Earth Engine username. Your username is whatever comes after users. So for me, my username is Ujjwal Gandhi. So if it's the first time you're saving something in Earth Engine and you hit the save button, it'll say choose a username. Be very careful in choosing the username. Make sure you don't make any typos or don't use a random username, because once you choose it, you can never change it. If you choose your username to be testing123, you'll always be known as testing123 in Earth Engine. You can never change it. So make sure the first time you're saving it, you can choose your username. If you have a username already, you'll be asked to say what repository you want to save it. A repository is a place where you can save folders and scripts inside of it. Logically, I have one repository for each course or each project. So you can have a repository saying my Earth Engine course, and you can save all your scripts there if you wanted to. Okay, so if you wanted to save some work that you've done, make sure you save it. You'll be prompted saying you can't save in my repository, save it to your own repository. And once you save it, you'll be able to share it. Now we'll explain how to do the exercise.
Yeah. For The exercise here, you see that we want to create list of top large cities in the world. So top 5 large cities, we already have the name. You can use these names on the list. So create a variable called large cities, and you can just have a list of these cities for this variable. So create a list. This is a variable that you want to use. You can just have a list. So just remember how can you create a list and use that, and you will print the list and you will see those 5 cities printed in the console. So just try this code, and for sharing, you can just click here at the arrow for it is beside get link. So just click on that arrow and you can just say get link.
So on the get link, there's a get link button, shareable snapshot. This is what you want. The other ones are not the right option. So make sure you use this. When you click this, it takes a snapshot of whatever you typed in your code editor and creates a static link that you can use. If you change your code afterwards, it will not be updated. It's a point in time where you click on it, whatever was typed will be captured into that link. And whenever anybody clicks on the link, they'll see the same code for that. We'll start working on script 2A now. The goal for rest of the module is to find some images from the Sentinel-2 satellite over your city of choice, apply some filters, create a cloud-free composite for that region of choice, clip it to your city, and then export the data as GeoTIFF file. So we'll have to learn all of those different skills, how to find images for a city for a specific time period, how to create a cloud-free composite, how to clip it, and finally how to download that images as GeoTIFF files. So that's what we'll learn step by step in each of the script. First, let's learn how to find dataset in Earth Engine. When you want to search for some data, you can go to the Earth Engine data catalog. The easiest way to access the data catalog is from this button here on your code editor. There's a help button. The first link here is user guide. This will take you to the main documentation for Earth Engine. Inside of that, you'll see a link called data catalog. This will bring you to the data catalog page. This contains the main page, which has all the datasets. The datasets are organized at the top by the 3 main remote sensing dataset, Landsat, MODIS, and Sentinel. You also have the data organized by different themes. So for example, if you're doing some climate research and you want some climate data, you can come here and say what datasets are available. This is also a good way to kind of browse and see what dataset might be useful for your work. You can also search for a specific data that you want. So if you say, I need this data, I want to check if it's available, you can directly search for it, or you can just browse for it. For this module, we want to access the Sentinel-2 dataset and work with it. So let's go to the Sentinel link here. This has got all the data from the Sentinel's Copernicus program. There is Sentinel-1, which is radar data. We have Sentinel-2, Sentinel-3, Sentinel-5P, and other derived datasets. We want to use Sentinel-2, so let's go here. And then we have 2 versions of this datasets. There is level 2 and level 1. If you remember from the introduction to remote sensing lecture, when the satellite captures the data and it's stored on the satellite, that is level 0. That's a raw data. The satellite providers takes this data, processes it, corrects for various kind of atmospheric effects, corrects for things like sun angle, the satellite look, and creates orthorectified georeference product. So this is the kind of the minimum level of product that is usable in the GIS environment. And that is the level 1 data. So level 1 data is orthorectified and corrected. The values of the pixels that you have is the reflectance of a pixel that is measured at the satellite. So if you have some material, it has reflected the sunlight, passed through the atmosphere, and whatever satellite measured, that's the value there. You can apply further corrections and create something called a surface reflectance data. You can use other data sets which tell you how was the atmosphere, what was the composition of atmosphere at that time, correct for that, and then say how would be the reflectance if measured on the ground. And that's what you want. Remote sensing will tell you what is useful to know what would the reflectance of a material on the ground. So this is the data that you want. Or whenever you have level 2 data, please use that because that is the most accurate representation of what was in the ground. In case of Sentinel-2, you can see that the level 1 data is available from 2015 onwards. Level 2 is available only from 2017 onwards. So again, you have shorter time series for level 2. If your project requires data for recent data, please make sure you use level 2. If you require a longer time series, you can use the level 1 data and it's still usable. Let me show you this. For this exercise, we'll use the level 1 data. I'm going to click on this. Then you come to this dataset description page. It tells you date range. It tells you the description, which is about what the data set is. It also links to the canonical documentation. If you want to learn more about the data set, you can use this. There's a band section. This is multispectral data. Each image has multiple bands, which is the reflectance as measured in different channels, different wavelengths. And you have those information here. You can also say, oh, I want to compute some index. I need the NIR and the red band. Okay, NIR is band 8, red is band 4. And you can learn more about the data set here. The most useful part of this page is at the bottom, where it says explore with Earth Engine. It has some code that is useful to just take this data and visualize this in Earth Engine. Whenever you are trying to work with a new data set, instead of writing the code to process the data yourself, you can start from this code here. This will immediately show you the data in Earth Engine and it'll tell you what are the bands and so on. So whenever you find a new data set, always come here and copy this. I'm going to copy this here, come back to my code editor, and I'm going to just paste it here. And I'm going to run this. For now, let's not worry about understanding this code. That's what the rest of the module is about. Right now, the idea is how can I find the data set in the catalog? How can I find the code snippet and run this in Earth Engine? And you can see when I run this, I see something on the map. Whenever you ask for map output, like an image or some vector data, Earth Engine will display this on the map here. When I ran this, it loaded this one layer in the code editor, and you can see this shows me the Sentinel-2 imagery over Lisbon. I can zoom and I can see what this data set looks like. Sentinel-2 is a 10 meter per pixel resolution. So each pixel represents 10 meters on the ground. Just fairly high resolution for a freely accessible global data set. And you have one image that is captured every 5 days. So from 2015, you have an image every 5 days for each interest. Just mind-blowing amount of data and the kind of things you can do with it. And you have ready access to this with Earth Engine and using the open data set. You can see the Sentinel-2 data set can show you buildings, roads, maybe large vehicles. It doesn't show people or small cars. That's the limit of the resolution of the sensor. But again, you have this really nice global data set in multiple channels. This is great. I like Lisbon, but I want to see the data for my city. Right? So how do I see this for my city? So here on Earth Engine code editor, we have this search bar. It says search places and datasets. I can search for a place. Let me search for the city of Bangalore in India. If I search for it, I get some matches. I click here. I get zoomed in to the city of Bangalore. And now I see some data for Bangalore. So it loads the Sentinel-2 data for the city of Bangalore. So this is great. Maybe I look at something and say, oh, I found something interesting. I want to share it with some colleague. I send them the script and say, look at my script. And then they click run. They go back to Lisbon. The reason they always go back to Lisbon is if I look at the last few lines of the script, we have this line here. It says map.setCenter X, Y, and Z. So it is always setting the map to be centered at this coordinate. I want this to be my own city. So if I go to Bangalore and say I zoom into some region and say I want map to be centered here. So once I find the place I want my map to be centered, I can find the X, Y, and Z coordinates for it. Here on the left side of the console tab, we have this inspector. I can switch to inspector, click somewhere, and you'll see that at the first section, we have a point here. It says, wherever you clicked, this was the longitude, latitude, and zoom level. So these are the coordinates of the place where I just clicked. Lat long, we all know, these are the X and Y coordinates. Earth Engine uses the Google Maps zoom level. That means when you zoomed out to the whole world, it's level 1. As you zoom further and further, it's level 2, level 3, level 4, and so on. And you can see approximated scale. So this is 20 meters per pixel scale at zoom level 13. You do zoom level 14, it'll be further and so on. So you can go up to zoom level 20. So 20 will be quite zoomed into the ground. 1 is all the way zoomed out. All right, so what I want to do is I want my map to always center here. So I'm going to make just one small change. I'm going to take this lat long. I'm going to replace it here. So I'll say map.setCenter X coordinate, which is your longitude, Y coordinate, which is your latitude. I'm just going to replace those with these two numbers and replace the zoom level to be whatever 30. Now, when I run the script, I'll always come here. Wherever I am, when I run the script, I'll always be centered to this view. So we learned how to find this dataset description page from the data catalog. We learned how to find the code snippet. We learned how to use the inspector to click and find the current coordinates and the zoom level of a place. And then we just made a small change to center the map around the area of interest that we have. Okay. Let's try this out. Meghna, you can explain the exercise.
Yeah, so for the exercise here, we want to find a Sentinel-2 level 1C dataset from the page. We want to copy paste the code snippet and we want to zoom through the city of your hometown. So you will just have to change the set center. You can just go to the Sentinel-2 dataset. I'll just show you the process again. So from data catalog, let's directly go to Sentinel. And here we have Sentinel-2. Here we see two collections, level 2A and level 1C. Let's go here. Here we have the script that we want to copy. We have the copy button here. You can just use this and paste it here. Okay. Now you have to just do this thing. Change this set center to your region. So I'll just show you on my hometown. So my hometown is Jamnagar. I'll just search and I'll use inspector. I have my coordinates here. I'll just change it. So you can set zoom level, whatever you want to, and just try different things and just see whether you are getting the view that you want of the satellite using zoom level and the coordinates here. So try this exercise.
Let's work on the next script. We got some code snippet and loaded the data, but let's now try to understand the script and kind of build the script from scratch, where we take a data set, apply some filters to find the images that we want, and then create a cloud-free composite. Let's work on script 3A. Again, when I'm building the script, you can just look here and understand the workflow, or we'll work on an exercise a little later on. You can see there's a search box here. It says search places and dataset. So instead of going to the catalog and kind of finding the code snippet, you can also search for the dataset here. So I can just search for Sentinel-2 in this search box, and I can just pick the dataset directly from here. So you can see I get some matches. I have this level 1 and level 2. Let's take the level 1 data. I'm going to click here, and it brings up the same dataset description page. And if I say I want this dataset, I can just import it directly. So I can click import, and you can see it added something on my script at the top. It says there's a var image collection, which is Sentinel-2 dataset. So now I have a variable called image collection, which is referring to the entire Sentinel-2 image collection. I can change the variable name. I'm just going to take this and rename it to S2. You can just click on it and rename it. So now I have a variable in my script called S2 that is referring to the Sentinel-2 collection. If you think about what this variable has, it has got every image that is captured by the Sentinel-2 satellite since 2015, literally millions of images. And this is scary for remote sensing people, because when you're doing remote sensing, you typically download a few scenes that you like, and you have those sitting on your computer. Here, you say, I have every scene ever collected everywhere in the world. Do your analysis. And now this can be quite scary. So almost all alternative scripts will start with a collection, and then we'll apply something called filters to find images that are interest to you. Because unlikely you want to work with every image ever collected everywhere in the world. Right? You want to find images for a certain time period over your region of interest, matching certain criteria. So let's learn about filters and how to find the images that you want. We'll learn about 3 kinds of filters. First, we'll learn about date filters. So I want to find images for a certain time period. Let's say we want to find images collected in 2019. So this is my goal. I want all images collected in 2019. I want to use a filter. Earth Engine has many filters that come in. So let's learn all the different filters that are available to us. On your code editor, we have this docs tab. The docs tab contains all the API functions that you can use. One of the core skills that I want to teach you in this course is how to browse and find the function that you need for your particular application. So you'll have to get comfortable browsing through the documentation. Let's look at the filters that are available to us. We have the module e.filter, which contains all the different filters that are available to us. And you can see there are hundreds of filters that allow you to do different kind of filtering. Go through this list and tell me what filter I can use to find images that were collected in 2019. Go to Switch Docs tab, open the e.filter section and see if you can find a filter that matches, allows us to do this. So you can see there's a filter here, EE filter date, start and end. It says filter a collection by date range. So you can give a start and end date and it'll give you a filter. So it says, if you do this, I'll give you a filter that allows you to do this. This date filter is what we need. So we can say, we want to find images from 2019, 1st Jan to 2019, 31st December. Right? We can use this to create a date filter. We have start and end date. Once you read the documentation, it says the start date is inclusive. That means it'll include the start date, but the end date is exclusive. That means whatever date you specify at the end, that date is not included. If I wanted all images in 2019, and if I say my start is 1st Jan, end is 31st December, the images collected on 31st December are not included because the filter excludes the end date. It's just how Earth Engine API function is designed. So again, read the documentation. In this case, we have to specify 1 day more. In Earth Engine, whenever you specify a filter, you always have to do 1 day extra. So I'll say, I will filter for all images from 1st Jan 2019 to 1st Jan 2020. And that will give me all images from 1st Jan till up to 31st December. Let's write the filter. So I'll just say, I'll create a variable called date filter. I'll create a filter. And you can see it's case sensitive. Is e.F.date. My start date is 19/01/01. I can specify them as strings. So this is my filter. I've created a filter that will allow me to filter for images collected in 2019. I have a filter. I want to apply it on my image. So I'll say, take my S2 variable, which is the full collection, and I want to apply this. How do I apply a filter? Well, I'll go to my image collection module because S2 is an image collection. And you'll see that there is a function called filter. It says apply a filter to this collection. So dot filter, and the input to this function is a filter. So I'll say S2.filter, and I need to give it a filter. We already have created a filter called date filter. So now I have this variable filtered, which now has only images collected in 2019. So we found a filter, created a filter object, and then we use that object with the filter function and say filter using this object. You can do this in 2 steps. You'll see a lot of code that just does it in a single step. Instead of first creating a filter, storing into a variable, you can just do something like this. Same thing. Okay? Instead of first creating a filter object and using that with dot filter, it just says you can do this. We now have this filter variable containing all 2019 images. Next, we want to do location filters. We want to find images collected over region of interest. So how do I filter for images that are collected over a specific region? I'll start with my filtered object. So filtered variable. So this one is here. So I'll say whatever images are in 2019, further filter it down to images that are collected over some region. Go and find a filter that I can use to apply that. So go to the e.filter module and see if you can find a filter I can apply to filter images that are collected over a specific region. Yes, filter.bounds you see here that says creates a filter that passes if the object's geometry intersects the given geometry. Now it says filter bounds with a geometry. I don't have a geometry, but I can create one. So let's use that filter. I can go to anywhere in the world, and Earth Engine provides us with some drawing tools. I'll just use a point here. This is add a point here. I'm going to click this, add a marker, and click on any city. So I'm going to click here on this city. You see what happened? I get one more import in my script called geometry. It's a variable named geometry, which is referring to this point here. So now I have a geometry, and I can use the filter and say, if I give this point geometry, it'll create a filter where it'll check the image's footprint and see if that intersects with that point. If any image's footprint is intersecting the point, you'll select that. So that's what we can use. You can instead also use a polygon and other things, but for now, let's just use a point. So we dropped a point using the drawing tools. We have a geometry, and I can just say EE filter bounds geometry. Now I have this filter to object that has got images collected over this point in 2019. Okay, so I've filtered from everything to only the images collected over this city in 2019. Let's further apply another filter. We'll apply a metadata filter. Each comes with certain metadata that the provider has given to you. What metadata does Sentinel-2 come with? Let's go to the dataset page. If we come to the dataset description page, we have the third section here called image properties. Every image in this collection has this many properties, which is the metadata that it comes with. And the metadata contains all sort of things. Things like cloudy pixel percentage. What is the cloud cover for this image? What was the quality? What was the solar angle? What was the product quality? Which satellite captured this? Was it Sentinel-2A or 2B? All of this metadata is given with each image. And you can use this to say, I want to filter using some metadata using this. So let's use this metadata and say, I want to find images which are less than 30% cloud cover. Yeah, so I'll say I want to find images having less cloud cover. I can further define this as saying we want to find images where this metadata is less than 30. So I want images with less than 30% cloud cover. Let's write our code. Filtered 3 will take the previous filtered 2, which is the variable having the data for 2019 over the city. Apply one more filter where this property is less than 30. Go and find a filter that I can use. Go to the docs tab under e.filter, see if there are filters that you can use to do this. So there is a filter LTE or LT. It says filter on metadata less than or equal to given value. And that seems like the filter we want. You have two things, the name of the property and the value. We can use this to do this. We can use LT or LTE depending on less than or less than equal to what we want. So let's just use E filter LT and say this property has to be less than 30. There's a question, why not use this other very interesting looking filter, E filter metadata? If I open this, it's in red. First hint why I should not use it, it's in red. If I click on this, it says deprecated. Don't use this. Use E filter, EQ, GT, LT, etc. So you found the correct filter, but it was an old API call that has been deprecated, and there are newer functions like this which has to be used instead. All right, so we're done. Let's print this variable filtered 3 and see what it contains. So if I run this, you'll see that this is an image collection with 30 images. So we started with millions of images, and then we filtered it down to 30 images that match this criteria. If I just look at the IDs of the image, you can see these IDs all are in 2019. So this is image collected on 4th Jan 2019, 9th Jan 2019. You can see it's every 5 days. You get a new image. If I open this image, you can see it's got some properties. Each image has this metadata. You can see the cloudy pixel percentage for this image is 0. Similarly, if I open some other image, you'll see the cloudy pixel percentage 0.25. So all of these images has less than 30% of cloud cover, and we found those images. If you load this on the map, you'll see all of them are over this region. Right? So we now found some images that match our criteria using this. We'll learn how to visualize this in the next script. This is about learning filters. So we just started with everything, applied the filters, and we finally found these 30 images that match our criteria. So you can see this can get quite cumbersome. You have to take the collection, apply a filter, store it in a variable, take the variable, apply another filter, store it in a variable, and so on. And this can also be error prone. Imagine by mistake I did filtered instead of filter 2. I'll get a wrong result. So instead of doing this, Earth Engine provides you with an alternative syntax where you can apply all the filters together in a single line. And that is called chaining. So we can chain multiple filters together, and the chaining operator is the dot. So let's rewrite this code where we can apply these functions together. So we'll start with the same code. So first we start with S2, apply a filter. But now, instead of ending my command with a semicolon, I said the command is not complete. It's still continuing. I remove the semicolon and I put my second filter. This says, take the S2 collection, apply this filter. Whatever is the result, apply this filter. And we can keep going. We can keep going and keep applying filter by adding this dot operator. So now we say, take S2, apply this filter, take the result, apply this filter, take the result, apply this filter. And only when we are done, we put a semicolon. Now we applied all of those together. Let me print this. Both of them are identical. You can see this is also the same images. It found the same images. So instead of doing all of this, we can now do all of this in together using chaining. And this is the preferred way, less error prone. You'll see a lot of code where you apply filter in sequence like this. So we can just do this instead. And this is how we can apply filters. There's also a useful function. There's something called, if I run this, I'll get a collection with some images. I can call this function called dot size, which will tell me how many images are there in the collection. Useful to kind of figure out, we had somebody said, okay, what if I have no cloud for images with less than 30% cloud cover? You can adjust this and say, I want everything less than 50% cloudy, and you'll see this number go up. If you say, I want only images which are exactly 0% cloud cover. Sorry, say I want exactly 0% cloud cover. And you can see there are only 9 images and so on. So the dot size is a function that will tell you how many images are there in a collection. Useful to just do some research and find out. Let's do the exercise.
Yeah, so for the exercise here, we want to find images for January 2020 on our region. So it should be a point geometry at your chosen location. So here you see that we already have a geometry. We are filtering the image, and if we run the script with the same conditions, we are getting 30 images for this date range and this geometry, which has less than 30% cloud. Here you have to just remove this geometry and create a new point at your chosen location. I'll just say my maybe hometown. So I want to see images from here, and let me just create a point. So you can just create a point over a region here like this. This is the sign that you are going to use to drop a point. So now I have this point geometry, and I'll have to change the date range suitable for January 2023. So remember that you have to, the end date is exclusive. So you will have to set it to 1st of February. And if you will run the script, you will see how many images you have with less than 30% cloud. If you are in a very cloudy region, you might have to change this. If you are getting 0 number of images, you just have to set this to a higher number. So maybe say 50% or something, and you will get some images because the region is cloudy and you are not having any images which has less than 30% cloud. So just try this, change the date range, change a percentage if required, and most importantly, just choose the point over your region.
Okay, let's work on script 4a. So far, we've learned how to load image collection. We loaded the Sentinel-2 level 1 dataset. We dropped geometry point on a region, and we applied some filters. We found this images. When we run this, we find that we have this images that we found over this particular region. So we found this 30 images that matched our criteria. So far, we've not even seen those images, right? Let's see those images. So we have 30 images, and we want to visualize this on a map. How do you load this? Let's go to the docs tab. On the docs tab, you have some functions under the map module. This map module has functions that control this map below. So if you want to do anything with the map, add stuff, remove stuff, change the zoom level, etc., you have to use the functions in this. There is a function here of map.addLayer. If you call this function, it says adds a given E object to the map as a layer. You can add an image collection, you can add a feature, you can add an image or a map ID. You can see there's 5 parameters. When you read the documentation, any parameter that are mandatory will be in the regular case. The optional parameters will be in italics. So if you see some italics, these are optional. That means you can skip those and there'll be a default value that will be used. So you can see we need to give all of this, but those are in italics. So we can just say map.add layer some object and it'll display that object. We have an image collection. Let's display this. We'll say map.add layer filtered. We see something, but it's not what you expect, right? You expected to see some nice, beautiful Sentinel-2 imagery, but we don't see that. We see some black. Why is that? Because when you ask Earth Engine to display an image, Earth Engine says, I don't know how to display this. You have multispectral images. So I have 12 bands of information. What should I display? You have data in very wide range of values. What value should I display on the map? It doesn't know all of that. So when you add a layer, you can see it's got added as a layer here. There's a settings button. You can click the settings button and it'll show the default settings that Earth Engine used to display this image. It says, I have displayed band 1, 2, and 3. I have so many bands. It just chose the first 3 bands. That is something that you may or may not want. Let's go back to our dataset documentation. Sentinel-2 has so many bands. What do you want to display? Computers and human eyes can perceive only 3 colors at once, 3 channels of information, red, green, and blue. So you can display any 3 bands in the red channel, green channel, and blue channel, and the resulting image will be displayed here. Let's create a natural color composite. So if you are flying over this region, how would human eyes perceive that? We'll perceive that where we'll put the red band in the red channel, green band in the green channel, blue band in the blue channel. These are called natural color composites. That means we want to display band 4, 3, and 2, and that will be our bands that we want to display for RGB composite. You apply this, still pretty blank. If you see here, it says the range of pixel values is trying to display 0 to 65,000. Why is 0 to 65,000? Well, if you look at the images, each of the bands of the images are data type int16, the 16-bit integer. It means the pixel value can store values from 0 to 65,535. That's the theoretical range of values that the data can be stored there. So Earth Engine says, I don't know what's the actual range of data. So I will just display this from 0 to 65,000. If you know the actual range, you can display that. We know that this is Earth observation data, all the pixel values, the reflectances of those bands, red, green, and blue, are typically between 0 to 0.3. That's a range of pixel values that are there usually on surface of the Earth. And we learned previously that the Sentinel-2 data is scaled data. That means instead of giving you values as 0.3, they give you 3,000. So the actual range of values that it's giving you will be 0 to 3,000. That's a kind of range of values that you expect to see in this region. So we say, let's just display this data from 0 to 3,000. And now when I click apply, you see something that resembles a satellite image. And now we can say, okay, this is what we saw. We can display this and we can see this data. Now, you might be thinking, how do I know 0 to 3,000? There's something that I learned over time, but how do I, if I load some new data, how do I know what's the range of values in this region? So one helpful thing you can do is when you load some data in Earth Engine, you can say, I don't know what's the range of values. Compute the statistics of this image and show me what's the actual range of values. There are different ways of computing statistics. The most common one used in remote sensing is 98th percentile. So it says, in this region, show me what's the range of values at the 2% and 98th percentile of values. So take all the pixel values, remove the bottom 2%, remove the top 2%, and what's the range? And you can see in this region, the values range from 618 to 2006. That's what was computed. And that would be a good starting point for you to say, this is a good way, good min-max values to see this data. You can see this data appears much nicely because I've applied a contrast stretch where the blacks are mapped to this, whites are mapped to this, and then you have a nice contrast stretch. So when you load a new data, you have to figure out what band combination you want and what's the range of values you want. Some of you may be thinking, this seems like a lot of extra work. I have never done this in my GIS software. So if I take QGIS, so this is my QGIS, and let's say I want to load some data. If I load the data, this is a Sentinel-2 image that I'm trying to load in QGIS. And once QGIS loads, you'll see that I don't have to do this, figure out what's the range of values. I see this nice colorful image. Why is that? Because QGIS, ArcGIS, and most desktop software will say, you want to visualize this data, we'll figure out those parameters for you. So if I open the parameters, you can see QGIS applied this 98th percentile stretch. It says I figured out the min-max values for all bands automatically based on this setting, 2 to 98th percentile. That's the same 98th percentile stretch that we had. So that's the reason you never do it. The software does it for you. If you want to compute those yourself or see them yourself, you can go to the properties and we can say, let's compute the histogram. If I see the histogram of, say, and you can see most of the values here, they are between 0 to 3000 here. And that's the reason we say most of the values are here, so you can use that as the starting point. So when you load a new data set, apply a 98th percentile stretch to get an idea of what the min-max values are, and then you can adjust it. This is only adjusting the visualization. It's not adjusting the data values. It's just showing how the data appears on your screen. So you say, okay, I've applied this. This looks really nice. And you send your script to your colleague, and they run it. What happens? Back to black. Because all the parameters we configured, they were not configured in code. They were configured in your browser. So if you want to configure this in code, we can see there is a second parameter called visparams. We can give the visualization parameters and define those in code, so they are always applied. Let's apply that. So I'll just say I will create a new variable for visparams. This is a dictionary that takes different values. You can say, I want this bands. You can give a list of bands. So I say, I want R, G, and B, red, green, and blue bands as my bands. I want my min value to be 0 and max value to be 3000. Now I define the parameters that I want for my visualization. I can supply them as your second variable. And now when I run this, you will see that this will appear nice in that min-max values that we chose here. You can see when you add a new layer, it's always named layer 1 or layer 2. The third parameter in this function is the name of the layer. So I can also give a layer name. I'll just say my filtered collection. And now my layer will be called filtered collection. Now, you might be thinking, we are looking at this image collection. What do you think is displaying? We have 30 images in this collection. What do you think this is being displayed here? So we have 30 images on our image collection. They're all in the same place. Earth Engine is not a 3D system. It can only display one pixel. So by default, it displays the topmost pixel. If I inspect this, you will see that this is what Earth Engine calls it as mosaic. So what you're getting is a mosaic where it just takes the topmost pixel of the stack and displays this. And if your topmost pixel is cloudy, well, that's too bad. This is how remote sensing was done, where you find images which are mostly cloud-free, you stack them on top of each other and try to create a mosaic of mostly cloud-free data. But there's a better way to do this. Instead of loading a mosaic, we can say, let's create a composite. Composite are now the preferred way of working with satellite data. Because of clouds, you have clouds and cloud shadows in almost all images. So instead of trying to find images which are cloud-free, you say, I'll take the whole stack of images. I have 30 observations on this pixel. I will just take the average value. And by taking the average value, you say, the shadows will have very low values, clouds will have very high values. The average pixel will be cloud-free. So I can just take an average and do the cloud-free. The shadows and the clouds are also outliers. So let's say that if you take the stack of images, your values will be like this. A typical value might be like 2000. First image has 2000, second image is 2100. Third image had a cloud shadow. It'll be very low value, like 100. Fourth image has a cloud. It'll be 9000. Fifth image has another cloud, 9500. Sixth image is cloud-free. So it'll be like this. So now if you take an average, they get affected by this very high and very low values, which are outliers. So in case of clouds and cloud shadows, average will not be a right metric to do. Instead, you will take something called a median. Median is you sort the values and take the middle one. And those are more robust towards outliers. So instead of doing an average, we'll do a median composite, where at each pixel, you'll get the median value. So let's just create a composite. We'll take our filtered collection can do dot median. Median function will create per pixel median value, and you can see this. This operation, is very data intensive, very computationally intensive. People do not do this on the desktop, because that means you will download those 30 images and crunch through millions of pixel values to get a median value at each pixel. Earth Engine, with its computation and this kind of lazy loading system, it can do this on the fly. So let's just load the composite with the same visualization parameters. And you'll see that Earth Engine will compute this in real time, the median value at all the pixels. And you'll see that that median value is likely to be cloud-free, because it will be not having those low cloud shadows and high cloudy pixel values. And you can see the tiles being computed on the fly across different machines, and they are streaming in as they are being computed. And you see this really nice cloud-free composite of the city. This is the median value of this each pixel observed through the year. We worked on this script. What we did was we started with the Sentinel-2 collection. We applied 3 filters. One was a metadata filter to find all images which are less than 30% cloudy. We've filtered for all images which are collected in year 2019. Then we filtered it by that images that intersect a point of interest. And then we just did a composite. So we had 30 plus images that we found, and some of them had cloud, some of them had cloud shadows. But in the whole stack, if we wanted a cloud-free version of that, we can just do dot median, and that will take per pixel median value and create a new image. And we could visualize this using the visualization parameters. Here in the visualization parameters, define what is the range of minimum and maximum values that we need to use. Here, the minimum value will be clamped to the black part of the band. The maximum value will be to the white, and will be applied a linear stretch between those. If you don't know what are the good min-max values, you can use the settings button here to compute a 98th percentile stretch or a 1 standard deviation stretch. That will give you an indication of what is the range of values that you see on your screen, and you can use that as a starting point. If you find that the images is low contrast, reduce the range. Reducing the range will increase the contrast between different features. If you find the images low contrast or very high contrast, expand the range. So here you can see the image is looking pretty nice. If I increase the range to, say, I will make it 3000, you'll see that the images will become less contrast. So if I say, let's make it 6000, and you'll see that your image will have lesser contrast, it will be dark. So if you see your visualization is very dark, you want to improve the visualization, shorten the range. Shortening the range will make those values appear in higher contrast. If you make it too short, though, you will see saturation and very high contrast. So for example, if I just made it to 1000, you'll see that the values 1000 above will become white. And that means you will see that it doesn't appear very nice, right? So again, whenever you're working the new data set, you want to create a visualization of the data. Start with the 98th percentile stretch to get an indication, adjust the range till you get a visualization. Once you start working with the data set, you'll generally get a good idea of what the range of values are, and you can use that in your starting point. For Earth observation data like Landsat, Sentinel, MODIS, most of the reflectance values are between 0 to 0.3 range. So that's a good starting point, and then you can adjust that based on the region you're working with. Right, we're going to do an exercise now to apply this concept and see how doing this median composite will be useful in doing change detection.
So for the exercise here, you see that we have the script to generate 2019 composite, and then we are adding the median composite to the map. We also want to create composite for 2020. So you will just have to apply the same script, just change the date range and variables accordingly, and you will be able to generate composite for 2020. Now we are doing it on some point here. We will be doing it on our chosen location like we did for earlier exercises. So here you can just remove this geometry, create a new geometry point at your chosen location. You have the script to generate 2019 composite, copy the same and try to replicate it for 2020 as well, and have both the composite here, have 2019 and 2020 both the composite, so that we can see the change between these two images.
The idea here is that you want to know how your region of interest has changed between 2 years. If you had clouds, you cannot compare both of them, because if there are clouds in one of them, then you don't know what happened. So first we'll create a cloud-free composite by doing the median compositing, and then we'll compare 2 years. And you can see how your city or your area of interest has changed over those 2 years. So go and try this out. Let's work on the next script, 5A. When you have images or climate data in Earth Engine, they come in as image collections. Earth Engine data catalog also has a lot of vector data in form of admin boundaries, hydrological boundaries, building footprints, and so on. Those come in as feature collections. So let's learn how feature collections are different than image collections and how to work with them in Earth Engine. I can use the search to search for data sets. I'm going to use search for this data set called GAUL, G-A-U-L. This is an admin boundary dataset that is produced by FAO. They have 3 versions. There is a admin 0, which is the country boundaries. So if you want to work at country level, they have boundaries for each countries. They have admin 1, so states or provinces. If you want data boundary of a state, you can use this dataset to get this. And then you have second level admin boundaries, which is the districts or counties, depending on where you are. Let's use this dataset, FAO GAUL 500 meters simplified. When I open this data description page, it looks similar, but not the same as our image collections. First, you will see that there are no bands. Images have bands. Vector data doesn't have bands. Instead, you have table schema. This is when you have a shapefile and you upload to Earth Engine, your attribute table becomes your table here. So this is the attributes of each feature that is contained in this data set. You have some descriptions of the data. And once we want to use it, we can just click import. This works the same way. When you import an image or feature collection, by default, it's assigned to a variable called table. We can always change it. I'm going to just change it to admin2. So now we have this variable called admin2, which is pointing to this feature collection containing all admin2 level polygons of the world. This is a global data set, and we can visualize it. So a lot of the functions that work with image collections, you can just use them the same way with feature collections. I can just say map.addLayer admin2. Map.addLayer can add any Earth Engine object onto the map. So let's visualize this. We have not applied any filters yet. So you can see this is all the admin2 polygons for the whole world. So you have all the districts and counties that are there. I can use the inspector and I can go and zoom into a particular polygon. I can inspect it the same way. If I inspect it, you'll see that this is a feature. So it's a single polygon and some attributes. And same way, I can go and select any other polygon and you'll see the attributes of those. Most likely, you don't want every admin2 polygon in the world. You want admin2 polygon for your region of interest. So how do we apply some filters to select the polygon that we want? Instead of us dropping a point or drawing boundary, this is the better way to do this. Let's say we want to select all counties in California. We're doing some analysis and we want to select all the counties in a particular state. So first step is I'll go to California and inspect it and see what the properties look like. You can see these are the different properties. Each county has this name stored in this property called admin2 name. Admin1 name contains the state name and admin0 name is the country name. I can apply a filter. So let's apply a filter to select all counties in California. So I'll say filtered admin2. What filter should I use here? All the filters that we saw in the e.filter module will work here. Go and find a filter that I can use to select all counties in California. And what code would I write here? We can use the e-filter EQ, the same filter we used earlier. It's a metadata filter. All of these are properties. So you can use a metadata filter to select some features based on the properties. And we can say, select all features where ADM2 name equals California. And let's add it to the map. I'm just going to add this, and we can comment out this whole layer. So now, if my filter works correctly, I should only see polygons from California on my map. ADM1, sorry. So we want to select all places where all the features where the state name was California, not admin2 name. So the correct way to frame this question was select all features where the state name is California. And now you can see all the counties where the state was California. and we could see this. When you add a feature to the map, you can define some wisp params. The only wisp params that you can use for displaying feature collection is color. So let's say I want to display this in a red color, and we'll just say name it selected. So now when I run this, you'll see those polygons rendered in red color and the layer name will be selected. We can further apply a filter. So for example, if my interest is to do some analysis for one of the counties, I can go and say, I want to do analysis for, let's say, San Francisco. I can come and inspect this here, and you can see that for San Francisco, the admin 1 name is California, the state is California, but the admin 2 name is San Francisco. So I can further apply one more filter and say, I want to now select the features where ADM2 name is San Francisco. And now you'll see that I have only selected one polygon. So we started with all admin 2 polygons in the world, gradually applied filters and selected the polygon that we need. So now when we want to do some analysis for San Francisco, we can just use this filter and we now have a geometry. We don't need to draw it or drop a point. We can just use this and do our analysis using that. One word of caution when using admin 2 datasets, in many countries, admin 2 names are not unique. So if I just did this, admin 2 filter, admin 2 name is San Francisco, you may have more than one match. For example, in US, almost all states have a Washington County. So if you say, give me Washington County, you'll have one in every state. So you have to make sure you apply filters for both admin 1. So select the state, and then within a state, select the further admin 2 name. So to select an admin 2 region, we apply both the state filter as well as the district or county filter and select the county that we want. Let's do a little bit more. So we have this filter where it selects all counties which are part of California state. What if I want to select all counties which are from California as well as Nevada? How do I select counties from both the states? Can you go and find a filter? Go and look at the docs and see if you can find a filter which allows me to specify more than one thing that I can use to match my features against. So the question is, how do I change my filter so I can select all counties in state of California as well as state of Nevada? Here we have this filter, EE filter in list. In list is a filter that allows you to specify a list of items, and any item that is contained in the list will match. Let's change it here. We'll say EE filter in list where admin 1 name is a list. So we can say match either California or Nevada. And now when we run it, this filter is going to match all the features where the state is both California and Nevada. And you can see now we have additional features that got matched. And again, this is why we need to learn how to use lists. And once you learn how to read the documentation and find filters, you'll be able to do things like that. Time for us to do an exercise, practice how to use filters and select your admin region of interest.
Yeah, so in this exercise, we want to filter the chosen admin 2 region. We have this feature collection for admin 2. If we run the script, we can see that our admin 2 features are loaded. Now I want to get one admin 2 boundary and want to add it with the red color. So I'll just filter this. So you can just go to your chosen location. Let me just search something here in my hometown and I'll see it's here. Use inspector to get the name. So here you have this feature, just expand all the properties and you will see what is the admin 1 name and admin 2 name for this particular feature. So you will just apply a filter on admin 2 to get this one. There are a few common admin 2 names in one admin 1 region. So there are multiple states with the same name in the country. So, or maybe in the different countries. So in that way, you will have to apply 2 filters. So apply filter on both the properties, say admin 1 name and admin 2 name. So say for this one, I would say admin 1, ADM 1 name Gujarat, ADM 2 name Jamnagar. So both the filter will be applied and then I'll get the Jamnagar polygon and then I can add it to the map with the red color. So try this, apply both the filters and add your admin 2 region on the map.
So the idea is you want to get the polygon for your region of interest. So let's say you live in a city, you want to know, I want this boundary of my admin2 region. So you don't know how it is spelled in the data set, what are the properties that they use. So first you zoom there, inspect it, and then you'll know what are the property names, what are the values that the data set has chosen for your admin region, and then use those to apply a filter and then display that polygon in different color than the base map. So try this out. Right, let's move to the next script. So far, we have used a built-in feature collection that comes in the Earth Engine data catalog. It's an admin2, admin1, admin0. You have many other boundaries. But let's say you want to use your own boundary. Maybe you want to use city level boundaries, or you want to use admin4 boundaries, which are not present in Earth Engine. Or we want the latest boundaries. If you are in a country like India, we like to create new districts every few months. So this data is come from 2015. We have a lot more districts. Some districts are merged and some are split. So you want to work with the latest data. Let's say you obtain a shapefile from an official source, and you want to use those polygons into Earth Engine. So Earth Engine can also import data into the system. So any data in the shapefile format can be imported. So let's learn about that. We're going to use this data set as an example of importing the data. This data set comes from GHSL, which is a very well-known population data source. They also publish a boundary of all the urban centers. This is the closest I could find to a global cities database. So if you think about, I want the boundary of my city, in your country, you may have your source for getting the municipal boundaries, which you can go to the local municipality or your local GIS agency and get this. But at a global scale, that doesn't exist like a unified cities boundary. So this was the closest I could find. This one is generated from a population data set. It's not cities, it's urban centers. So they say, which is the urban agglomeration, which consists of a high population areas, and then they digitize that using from raster data, and you assign a name to it. So global data set, good proxy for like cities of the world, and we can download this. We have a process version of this data available here. So we're going to go and download this shapefile. I'll also share the link to this in the chat if you want to just download it directly. The full version contains like 100+ columns. We just removed some of the columns that are not needed. So I've downloaded this data onto my computer, and you can see I have the zip file. I'm going to unzip it first. And you can see this is a shapefile. For the folks who are not from GIS domain, a shapefile is not a single file. It consists of multiple files. They all need to be present for the file to have all the information. A shapefile needs to have at least 4 files: SHP file, an SHX file, a PRJ file, and a DBF file. There can be other files. They're known as sidecar files. You can have many other files, but at least these 4 files are required. This file is now on my computer. I downloaded it from some source. I want to use this in Earth Engine. First, let's look at it. File in a GIS. I'm using QGIS here. I'm going to just show you what this looks like in my computer. So this is the shapefile as it exists on my computer. You can see it has got different cities, boundaries. If I open the attribute table, we have the different cities, names, their countries, and we also have information about population and so on. And you have a global database of all the urban centers of the world. You can see the boundaries are a little jagged because they've been kind of vectorized from population raster. So they are not smooth, they're not the actual municipal boundaries, they are derived from a population grid. But again, you can use any polygon data set instead of this. If you have access to a better version for those countries, you can use that. For now, we'll just upload this and we want to use this. So if I wanted to kind of create a composite for city of Bangalore, I would not draw one, I would just use this polygon and say, I want this polygon and this is the city of Bangalore. So we'll upload this and we'll use this in Earth Engine. Let me first demonstrate the process and then you can try this out. I'm going to switch to the assets tab. You have in the scripts tab, there's a third tab called assets. This is where you will upload data to Earth Engine, and all the data that you uploaded previously exists here. If it's the first time you're uploading something to Earth Engine, there'll be a button saying that create my asset root folder. So you can go and click that button, it'll create a folder. Once you have this, your root may start with users / whatever your username is. This is the old style asset roots. The newer, if you have a newer Earth Engine account, they are linked to Google Cloud. So those will start with project / the name of the project that you have. Either one is fine. You can use either one of them. All users will get 250 GB of free storage to upload data to Earth Engine. If you go to any of your asset folders, there is this button right next to it. It says quota usage. If I click on it, it'll show you how much quota you have and how much you've used. So I have 250 GB of quota and I've used 54% of those. You can upload images or vector data up to that much amount to Earth Engine. So we have the button here. Let's upload some data. What can you upload to Earth Engine? You can click this new button and you can see some options here. You can upload an image in the GeoTIFF file format. So if you purchase some high resolution imagery and you have data with GeoTIFF format, you can upload that. If you have some data that you want to work with in Earth Engine in GeoTIFF format, go and upload that. It'll be a private asset that will be in your Earth Engine account and you can run all Earth Engine functions on it. Or you can upload shapefiles or CSV files. So both of them are possible and we can use them. We can upload shapefiles in vector data in shapefile format or a CSV table format. Let's use this option, shapefile. It says select files. You can browse to the folder that we have unzipped our file to, and we just select all the sidecar files. Remember, shapefiles need at least 4 files, SHX, SSP, PRG, and DBF. So we'll select those 4 sidecar files and they'll be shown here. It accepts shapefiles in zip format. So sometimes you'll get a shapefile which is zipped containing all the files. I strongly recommend you unzip it first, because if your zip file contains some additional file, which is not any of the supported extension, your upload will fail. So a good practice is always to unzip the shapefile first and manually select those 4 sidecar files that you need to create a complete shapefile. Okay, so we have shown our file here. You can choose your asset root, and by default, it'll give the name of the asset here. And once you've chosen this, you can just click upload. I'm going to upload it to a subfolder. So once you decide the name of the asset and you have chosen those 4 files, you can click upload. You'll see your task tab light up on the code editor, and it says there's an unsubmitted task. This is, at this point, the files are still going from my computer to the Earth Engine servers. It takes a while for the files to be uploaded. Once the file gets uploaded and this gear starts spinning, that's a point where I can turn off my computer and nothing will go wrong. Files are there in Earth Engine servers. It takes a few minutes for Earth Engine to process that. It's doing error checking, it's doing validation, it's copying the data that you uploaded into the Earth Engine servers in the format that they use. So it takes a few minutes for the data to be processed. And once it's ready, you'll see a tick mark and saying your asset is ready. Till the gear is spinning, you'll have to wait for the asset to be available. So let's try this out. All of you can download this zip file. It contains all the city polygons of the world. Make sure you unzip it to a folder first. Do not upload the zip file directly. Please unzip it. Once you have the folder on your computer, switch to the Assets tab, click New, Table Upload Shapefiles, go and select all the files that you have unzipped. You need to select at least those 4 files. You can select the CPG file if you need to, doesn't matter, but at least you need these 4 files, and then you can keep the default asset name and start your upload. You can see my asset has been ingested. You can see box has a tick mark next to it. It took about 3 minutes for my shapefile to get ingested. It may take a little longer or shorter depending on the traffic on the Earth Engine servers, but this takes about 5 minutes on average. Let's see what happens once the upload finishes. So again, you can pay attention to my screen. Once you upload data to Earth Engine servers and it gets ingested, they appear in your Assets tab. So if I switch to my Assets tab and browse to the folder where I uploaded it, you'll see the asset appearing here. So here, the one that I uploaded is here, GHS Urban Centers. I can click on it. It'll bring up the dialog, which has more information about this asset. You can see you have an asset ID. This is a unique ID that is assigned to each data that you upload. We have the file size and number of features. This one has 13,000 polygons. You can also look at the attribute table. So this is individual features, and you can just go and check that. There's a share button here. If I click on it, it brings up a sharing dialog. By default, anything you upload to Earth Engine is private only for you. You can mix it with any public domain data like Sentinel and Lancet, etc. But this asset will be accessible only to you. It's the same sharing mode as Google Drive, where you upload something, it's only private to you. You can choose to share it with others. So if you're working with a colleague, you can enter their email and give them access, either read or write access to it. or you can click this button, anyone can read. If you click anyone can read, that means anyone who has a script which uses this asset will be able to read that asset. So if you're sharing a script which uses an asset and asking for help in a public forum, make sure you check this box, anyone can read. So your asset is public and others can run that. We learned about sharing. The default uploaded assets are private by default. You can choose to share it with a colleague or make it public by checking the anyone can read box. If you want to use this in your script, there's an import button here. I can just click import and you can see the asset gets imported to your script just the way you could import a feature collection or an image collection from the data catalog. And it's assigned a variable called table. And that's it. Now you are able to use this asset just the way it was as it was a feature collection in your data set. So let's just try this out and see what this region looks like. I'm going to change this variable name to be urban. And let's just add it to the map. Add this to the map and saying map.add layer urban. And now you can see the polygons in Earth Engine. These polygons were uploaded from the shapefile that we had on a computer and uploaded that. And now you can see this has the polygons that we needed. You can use them as the same way as before. I can click on any polygon and I can see the properties of this. I can apply filters. So let's say I wanted to extract the feature for the city of Bangalore. I can apply a filter. I can say, take the urban feature collection, apply a filter where the name, so this is the property, urban center, name, main. So this is property contains the name of the city. And we can say this one should be the city of Bangalore. And now I can add it to the map. And you'll see that this is only the polygon for the city of Bangalore. So now if I wanted to do some analysis for a polygon, I don't have that in Earth Engine. I can upload a shapefile, apply a filter, and then I can use that polygon that I need for my analysis. Let's do an exercise to work with the data we just imported. You can choose to work with the asset that you uploaded, or you can use my asset, which I have made it available to everybody in the script. If you choose to use your own asset, make sure you code to the asset and share it so that others can read it. So if you're using your own asset, make sure you go and click the share button here. Before you click the share button, wait for this to load. Once this loads, it takes a few seconds to load. And once it's done, you can click the share button and make sure it is readable by all. So you click this button, otherwise we won't be able to run a script. Meghna, you can explain the next exercise.
So for the exercise, this urban is the asset that you have. So if you have imported your asset, you can continue working with that, or you can use the same urban asset from this repository. And here we want to select large urban centers from the this feature collection that we have. And for that, we need to apply two conditions. One, to select the name of the country, and another is to get the population at the centers with population greater than 10 million. So here, if I just see the first feature from the collection, you see the property that this is the property which has country name, and this is the property which has population. So you have to apply a condition to select the name of the country on this one, and to apply the population condition which is greater than 10 million on
1
this
million.
particular.
I think this one is 1 million.
Okay. Yeah. So just apply these two conditions. One should be equal to filter, one should be greater than filter on your imported asset, and you will see large urban centers in your country.
So the idea is pick your country wherever you live, and you want to display or select all large cities, any cities having more than 1 million population. The P15 property contains the population as of 2015. That's in the database. So just select all large cities and display them on the map. So far, where we had some point and we wanted to create some composite for that region, we were able to use that point as a geometry and apply some filters. But we don't want to do that. We have the actual shapes of our cities. So instead of dropping a point or drawing a geometry, let's just use that actual shape as our geometry. We have our uploaded file that we imported as an asset. We have that in the urban variable. I'm going to comment out all of the script for now. So command / or control / comment it. And I'm just going to add the map.add layer urban. So this is all the urban polygons that we have. We'll pick a city. So I'm going to pick the city of Bangalore here. Instead of this geometry as a point, we want to actually use this polygon as geometry. So the first step is for us to apply a filter and select that polygon. So I'll apply a filter. We'll say, take the urban collection, apply a filter, use the EQ filter on this property, urban centers name main. And this has to be equal to whatever city that you want to extract. You check if that worked fine. So I'm just going to add only this. And if that worked, then I only get the polygon. Now this object is still a feature collection. What we want is a geometry so I can use it in my filters and other places. To get the geometry, we can use this function called dot geometry. When you run dot geometry on any feature collection, it gives you the union of all the features geometry that exist in that. Since our filter collection is only one polygon, this geometry will be just the polygon of that. And I can just add it to the map and verify that this indeed is the geometry that we want. So now we have the geometry, which is a polygon object that we've extracted from this feature collection, and I can use this geometry in my analysis. Let me just display this in, let's make it black, and I'll just say this is my geometry. Now I'm going to uncomment the rest of the code. We start with Sentinel-2 collection, apply a filter, and do a median composite. Let's just display this image. I'm going to display this image, which is a median composite. I have the RGB Wisp params, and I'll just say this is my composite. Just for reference, I'm also going to display the geometry that we had selected on top. What this filters did was selected all Sentinel-2 images that intersected that particular geometry that were collected in 2019 and had less than 30% cloud cover, and it created this composite. So we got a composite that was created from all the Sentinel-2 images, but we still have pixels outside of our geometry, which is something that you may or may not want. Why you got pixels outside the geometry? Well, because the Sentinel-2 images are very big. They're 100 kilometers by 100 kilometers. It just gave you all images that intersected with this polygon. So most of the time you said, I don't care about pixels which are outside of my geometry. I don't want to even see them. If you want to not see them, we can do clipping. So let's learn about this function for clipping an image. We have this function called clip. So I can take my image and say dot clip and give it a polygon geometry, and it can clip that. So now I'm going to clip it and display only the clipped image. And this time you'll see that now I have pixels that are only part of my polygon. So we started with all the Sentinel-2 images. We started with all the polygons of all the cities. We filtered down to the polygon that we need, extracted its geometry, used its geometry to filter the Sentinel-2 collection, created a composite, and clipped it. And now we have created a nice looking composite for the region of interest. And in the next step, we'll show you how to download this to your computer so you can take this and do some analysis. When you are doing stuff on a desktop or a traditional remote sensing processing, clipping is the first thing that you always do. You get an image. Even before you do any processing, you say, let me clip that first. That means I have lesser number of pixels to work with, I have lesser computation to spend, and they'll just overall speed up things. In Earth Engine, do not do that. In Earth Engine, if you clip your stuff first and do your analysis later on, that actually slows down Earth Engine. The way Earth Engine is structured is it works best if you do not clip stuff till the end. So good practice in Earth Engine is to only clip stuff when you want to display or export it. Otherwise, anything else you do, if you want to compute some statistics, if you want to do some analysis, all those functions will ask you, what is your geometry? What's your area of interest? And you'll do compute statistics only for that. You don't need to clip your image for doing that. So do not clip stuff unless you want to display this or export that. So if you see in a lot of the code that I have written in the user guide, clipping is always the last step. Do not clip stuff in the beginning of a script. That is actually counterintuitive, but it'll slow down your script. All right, let's do our next exercise, 7C. Now you can explain the exercise.
Yeah. For the exercise here, you see the script here, which is clipping the image for Bengaluru. And let's just run and see what it gives. So it is giving you clipped image for Bengaluru, and it is based on this urban area that we have selected from the feature collection. Here, your exercise is to clip a city of maybe your hometown or any other city that you want to have image of. So just repeat this for your chosen city. You can just change the name of your urban area here, and you will be able to see the clipped image after running the script. If you don't know the name yet, you can just add the urban feature collection to the map and use inspector for your urban area, and you can see what is the name exactly against this property. So this is how you can check name of your urban area, and just change it here and you will see the clipped image here, or just display it and share your script.
Yeah, you want to create Sentinel to composite for your city. So first, add the whole urban collection to the map, inspect your city polygon and see what's the name, change the name there, and it'll extract the geometry of that city. And the rest of the script should just work as it is, and you should see the city composite displayed. You can also add one more line. Now you can explain the map.center object. So there is one more function called map.center object, which can zoom to a particular geometry. So many times you have a script and you said, I don't know where the polygon is that I've selected. Center object is similar to zoom to this feature. So you can give it any object and the map will be centered to that object. So you can say map.center object clipped or map.center object geometry. And when you run it, it'll just go and zoom to that. So you can see map will just go and center that. So that's useful to add to your script as well. It's the map.center object if you want to try this out. So far we have created a Sentinel to composite for your region of interest. We uploaded a shapefile, we selected a city boundary, we used it to filter images that intersect that region from Sentinel to satellite for 2019. We created a median composite, we clipped it, and we have this really nice, beautiful looking imagery that is displayed here. This itself requires a lot of computation. If you had to do this on a desktop, you have to download literally hundreds of gigabytes of data, spend hours crunching that median composite, and then you'll have those results. Instead, Earth Engine is able to do this in real time, and that's great. Earth Engine can also do a lot of computation on that, but maybe you say, I have this data, I have written my code in R, or I have some other software which can take this data and do further analysis. So I want to download this from Earth Engine. Earth Engine is a completely open system. That means at any point during your analysis, you can download the result, either an intermediate result or a final result. You can export that. So now we have this image and I want to download that. Earth Engine allows you to export this data as GeoTIFF files, and you can download it and then use it along with any other software that you need. I always recommend people, when they start using Earth Engine, do not try to do everything as you're learning Earth Engine. Some of the stuff might be more complicated. As you build your skills, you can try implementing more and more of that. But just being able to pre-process, get imagery, and download it from Earth Engine will save you a lot of time. So start doing this right away, and then you can use the results in your project, in your existing workflow. And as you develop more skills, you can start implementing more features from your data processing. Let's see how we can export this data. Let me just print this image first. I'm going to print this clipped image. If I print it, you can see this image has 16 bands. These are all the 16 bands that come with Sentinel-2. Some of them are spectral bands. Some of them are QA bands. The QA bands contain information about cloud mask and quality, etc. You likely don't want them in your output. It may be that you don't want all the bands. Maybe you just want to download 1 or 2 bands of image. So first step to do is let's select the bands that we want to export. So I'm going to create a new image called export image. I'm going to take the clipped image and use the select function to select the bands I want. You can give the name of the band you want. So let's say I want to export the red band. If I use this function select before, let's see what happens. So I had an image with 16 bands, and now I get another image which is just 1 band. So I can select a single band from the image if I wanted to. If I want more than 1 band, instead of just the name of the band, I can give a list of bands. So if I want to just select band 4, 3, and 2, so R, G, and B bands, I want to export, I can just give a list of bands in the select function, and I get an image with 3 bands. So the select function is quite flexible. It can take a single band name, it can take a list of bands, or it can even take a pattern. So here I want all the spectral bands which start with B, but not the QA band that start with QA. So I can say, select all the bands which start with B. I can give a pattern like this, B dot star. If I say B dot star, it says, I'll select all the bands which start with B. So depending on your requirement, you can select one or more bands that you need to export. And once you're ready, you'll be able to export the data. So let's say we want to export all the image with all the B bands. To download an image, you need to use the export function. Let's go to the Docs tab. Let's search for export. You can see there are quite a few functions for exporting. You have functions for exporting images. You have functions for exporting tables. So if you have some feature collection and you want to download that as shapefile, you can do that. We have an image. So I can see this one is an image and you want to export that. So I'm going to look at this section under export image. I have 3 functions. The first one says export image to asset. If I want to take an image that I've analyzed and created in my script and put it back into Earth Engine as an asset, I can use this function. If I run this, whatever result I've created will go back into Earth Engine as an asset, which you can use in your other script or share with a colleague. This is recommended where you have a very large scale analysis that you want to do, and your analysis involves multiple steps. Instead of having a script that does everything, you do step 1, export the result as an asset. Once the export finishes, import the asset, do the step 2. And that means you have a pre-computed asset, you don't have to compute it every time. This saves you a lot of time and effort, and also a best practice for making sure you don't exceed the limits of memory and computation that Earth Engine provides. If you're working a project and you say you have a team, you say, I'll do part 1, you do part 2. So you do your part 1, export the result as an asset, share that asset with your colleague, they'll take that, do the part 2. So asset is useful. We'll use export to asset later on in our module 4. There's another option, export image to cloud storage. Google Cloud has a product called Cloud Storage where you can store large files. If you're using Google Cloud and your other teams need data on Google Cloud Storage, you can export your image there. Google Cloud Storage is useful where if you want to export really large assets. So let's say you're working on a national or a global scale analysis and you want to export something that may be in terabytes in size. You can choose to export it to Google Cloud Storage. Once the export finishes, download the data and then delete it. And you'll pay only for the time and the storage that you used. So if you want to get a 1 terabyte storage in Google Drive or other places, you'll have to pay for a month or a year. In cloud storage, you pay for the minutes of storage that you used. So it's a good practice to just, if you want something large storage, export it to cloud storage. Once the export is done, delete the data, and you will only pay for the time that you consumed the cloud storage. The third option, export image to Drive. This is what most of you will be using. All of you have a Google Drive account that comes with your Gmail account. You have 15 GB of free storage available there. Some of you have more storage through your institution or your company. And when you export the data from Earth Engine to Google Drive, it'll go and sit in your Google Drive. And whatever storage you have, it'll consume that storage. This is the preferred method for exporting data. And once it's in Drive, you can download it. There's one option that is missing from here, right? There's no export image to my computer. Right? Most of you would say, I just want to download to my computer. Why do I have to go through Drive or cloud storage? The reason is some of these exports can take a long time. If you're trying to do a very complex analysis and you're exporting something for the entire country, export might take 5 hours. You don't want to be connected to Earth Engine server for 5 hours. But the Google Drive and cloud storage, they're all in the cloud. They're connected to each other. So once you run an export, once the export starts, you can just close your computer. Once the export finishes, a new file will magically appear in Google Drive. And Earth Engine can do that without you being connected to the servers. And to enable that, you have only the export image to Drive option. So let's use this function and export this image that we have selected into our Google Drive. All right, let's use this function. This function is a scary looking function. We have to fill all of these parameters to be able to export an image. And this is when many of you will just get stuck and say, why can't I just get a button which downloads this image? Why do I have to write this really complex, scary looking function? I'm going to teach you some tricks that will help you fill all this parameter in an effective and easy way. Once you learn that trick, all this function will be much more easily accessible to you. So let's try this. Before we start filling the function, you need to learn one shortcut for autocomplete. Earth Engine gives you a shortcut called Control plus space, which is autocomplete. This will fill the function names automatically so that you don't have to type the full function. Super helpful. Also, Command plus space on Mac. Let's see how it works. You can type the first few letters of a function. Actually, on Mac also, it's Control plus space. So you can use Control plus space, type first few letters, and then say Control plus space. It'll give you a pop-up of all the functions it matches. You can use your arrow keys and select the function, and then you can arrow keys to select the function. So now any API function, you can use control space and it'll autofill that. What's more, once you have filled the function name, you can use control space again, and it'll fill all the parameters you need. So you don't need to kind of look at the documentation. And this works on all functions of the API. So for example, if I wanted to do some median, you type MED and then, just do median. So control space will autofill all the API functions. So if you want to write a function like this, we'll say export image, control space to autocomplete, use arrow keys to pick the function that you want, and then control space again to fill all the parameters. Now we need to specify all the parameters we need, and then only the export can start. There are some parameters that are required. Many of them are optional. You can see many of them are optional so that you can skip those. If you want to specify them in order, you will have to specify them null or have some default value. If you have a function that takes a lot of parameters, but you don't want to specify all of them, then it provides you yet another way where instead of specifying them one after the other, you can specify them as a dictionary. So I'm going to start a dictionary with a curly bracket and then start writing the value of each parameter with the key value pair. So I'll say image. What image we want to export? Say export image. Next parameter, description. This is the description that will appear in the task tab here when you are exporting. Just if you have a lot of tasks, you can differentiate them. So I'm going to write that as composite export. Remember, the description doesn't like spaces, so you can have underscore but not spaces here. Next, folder. When you run the export, by default, the new file will be created at the root of your Google Drive. You can optionally give a folder name so that exports go to a folder. I don't like my Google Drive cluttered with Earth Engine exports. I always give a folder name. So all my Drive exports will go to this folder named Earth Engine. So again, it doesn't clutter the rest of the Google Drive. File name prefix. When you export an image, the extension will be .tiff because it's a GeoTIFF file. Prefix will be the name of the file. So you can give the name as composite. So my output file will name composite.tiff. Dimension you typically don't need to give, so I can skip that parameter. This is the advantage of giving the parameter as a dictionary. You can skip the parameter you don't want to specify. Region. All your exports must give a region. What's the region of our export? We'll say geometry. You might think, I've already clipped my image to geometry. Why do I need to give region again? If you skip the region, when you export it, Earth Engine will say, I don't know what region of the image to export. It'll say, what is the region that is visible on the map? When the user ran the export, I'll only export that. So if I skip the region parameter and exported this, I'll only get this rectangular part of the image that is visible on the map when I exported this. And this is a very common problem. Many times users will write to me, I'm trying to export and I get a rectangle, small rectangle of the whole image. And I don't even open the script. I said, you forgot to specify the region parameter. So make sure you always specify the region parameter, which will be the region that you want to export. Scale. What is the resolution that you want to export your images? This scale is equivalent to the pixel resolution of your image. What is the pixel resolution of Sentinel-2 image? So let's just go and take a look. Let's check what is the resolution of Sentinel-2. Some bands of Sentinel-2 are 10 meters. Some of them are 20 meters. Some of them are 60 meters. You have to specify at what resolution do you want to export your data. Our image contains all the bands from 1 through 12. If I give 10 meters as the resolution, the 10 meter bands will be exported as it is. The 20 meters band will be resampled, upsampled to 10 meters. And I'll get those as 20 meters. 60-meter bands will again be resampled to 60 meters. If I give my scale as 20, all the bands will be resampled to 20 meters. So depending on what you want, typically you use the native resolution of the image. So 10 meter is this resolution of the RGB and the NR bands. So we use that, and all the bands, other bands will be upscaled to that. CRS. What's the projection that you want to export your data in? By default, the projection of the first image will be used, first band of the image will be used to determine what's the output projection of the data. You can also specify a specific CRS that you want. So let's say I want my output image to be created in a specific UTM projection. I can give the EPSG code for this, and all my images will be reprojected and resampled at 10 meters in this projection, and my output file will be in that projection. If I skip this, it'll be whatever projection of the first band of the images is, and it'll be used. Right now, I'm going to skip the CRS. Max pixels. By default, Earth Engine will stop your export if it exceeds 1 million pixels. If you're trying to export something and it's more than 1 million pixels, Earth Engine will stop your export, you'll get an error, too many pixels. This check is there just to prevent new users from accidentally exporting large images and suddenly finding out that their Google Drive is full. But now that all of you know what you're doing and you know exactly how, what image you want to export, you can just set it to a very high number. So I typically set this number to be a very large number, 1 followed by 10 zeros. And that means you'll never run to this limit. It's not that Earth Engine cannot export, it can export any large image. It's just that if you don't specify this parameter, the default value is 1 million pixels and your export will stop. So let's specify this high number for this. The rest, I can just skip those parameters. Close the dictionary, and I'm done with my export function. So using the autofill in a dictionary, I can specify each parameter by its value. It makes my code more readable. It allows me to fill these parameters one by one and much easily. And my resulting code is less error prone because I have given the name and value of each parameter. Once I run this, let me run this. You'll see once I run this, the task tab will light up. It says there is a task that is unsubmitted. So its export is still not started. I click run. One more confirmation. It says I'm going to export this data at 10 meter resolution to Google Drive with this name. Are you sure? And when I say run, Earth Engine will start the export. And once the export starts, you'll see this task with the gear that will start spinning. And once the gear starts spinning, you can now close your browser, close your computer, go to bed or go to lunch, whatever. Whenever the export finishes, the file will magically appear in your Google Drive, and then you can download that to your computer. One more time, I'm just going to do this again till you think of the questions you have. So I'm going to do export image, control space to autocomplete, control space to fill parameters again, specify the image that we want. This is my export image. Description, I can give a description to help me differentiate different export tasks. It can not have spaces. Make sure you don't use spaces. You can use underscore. A folder, this is a subfolder where all your exports will go. I always use this one folder, Earth Engine. I also recommend you do this. I'll tell you why. This also has one more advantage where you can automatically download data from that folder to your computer. File name prefix, this is the name of the file that I want. Always give the region parameter. If you forget it, only the part that is visible on the map at the time of export will be exported. So make sure you always give the region, whatever geometry you used, even though you clipped it. So you still have to give the geometry. Scale is the resolution at which the data will be exported. CRS is the projection of your output image. Max pixels, always set it to a high number so you don't run into the default limit of 1 million pixels. And once you're done, you can run your script and your export will start. The question is about how many exports can I run concurrently? What if I start 100 exports? How many will run together? Who manages the queue? It's a good question. You can start as many tasks as you want. As you start more tasks, they'll be in the queue. They'll be executed in the order that you started them. As the tasks are running, Google manages the queue. Typically, you have up to 3 tasks that will be executed concurrently. So if you have 100 tasks, the 3 tasks will be running. As soon as one of them finishes, the next one will start and so on. And you can see your task manager. If I open this task manager, it shows you what tasks are in the queue, what are being run, and so on. You can also, if you started accidentally some 100 tasks, you can go and bulk cancel those tasks if you need to. So it manages that. If you have a lot of exports, typically a good best practice is to split your data export into smaller chunks. People typically, if you're exporting an entire country, you will do export for each admin 2 region, or maybe each admin 1 region. So you have, let's say, 100 admin 2 regions in your country. You'll have 100 exports, which is exporting the data for that admin region. This allows Earth Engine to, again, instead of doing one large export, which might take 5 days, you do a smaller export, will finish in a day, and then the next one will go on. So it just, easier for you to manage that workflow. Also, if something goes wrong, it'll fail faster. Instead of you waiting for 4 days and find out, oh, there's some problem, you will know the details faster. So good practice to split your region into smaller chunks and export them as separate tasks. One thing that you should never do is, let's say you have a deadline tomorrow and you want to export 100 tasks. You start your task and 3 are executing. You say, I really want my task to go fast. Don't create another Gmail account, sign up for Earth Engine, and start your other task from another account. Many people do this just because they want to utilize more resources. Your resources are capped per account. So people think that, okay, if I start the task from another account, I can utilize more resources. You'll be able to, but then Earth Engine now has a detection system. Say this user is splitting their workload across different accounts, and your accounts will get blocked. So it's against Earth Engine terms of service to run tasks across different accounts. So if you want to do something, use your own account. It'll be in the queue because there is a resource per person, per user that you need to adhere to, and it'll use that. You can see my export finished. I can click this down arrow and learn some more information about it. It also shows how much computation I use. This is useful for commercial users. If you're a non-commercial user, it doesn't matter. You don't pay for this. Commercial users will pay for this. You get charged some dollar amount for some EECU usage, and this shows you how much EECUs were consumed for your particular thing. So just something that you can pay attention to. Once it's done, I can click Open in Drive, and it'll show the file that I just created in my Google Drive. And you can see this is the composite file that was just created. And I can now download this to my computer. So it's going to go and download this file as a GeoTIFF file on my computer. And then I'll have those pixels on my computer. I can do something with it. So this is the workflow. You do your work, and then you export the data to your Google Drive. Once the export finishes, export may take minutes, hours, days, depending on what you're trying to do. Once it's done, you can just download the data. See the result in QGIS. I have my composite that we just downloaded. I'm going to load it into QGIS. And you can see it's a fairly large image with a lot of pixels. This QGIS takes a while to load and render all the pixels. One of the things you should understand is we have this multispectral image. When we exported this, we are exporting a raw image. That means we have the actual pixel values for each spectral band that were exported. When you load the image, it may look different than what is appearing in Earth Engine, because QGIS or ArcGIS will apply their own visualization parameters by default. So many times people say, oh, I loaded this into ArcGIS. It looks completely different than what is in Earth Engine, because QGIS or Earth Engine will apply their own visualization parameters. Once it loads, I'll show you that if you apply the same viz params that you applied in Earth Engine, it'll look the same. But now you have those pixels on your computer, and you'll be able to do what you need. I want to share one tip with you. When you exported this, you want to download this to your computer. If you are on a Mac or a Windows machine, you can go and install the Google Drive application on your computer. So I've installed the Google Drive application on my computer, and I've configured so that it's linked to my account, and I've configured so that anytime there's a new file in this Earth Engine folder, it'll automatically sync that folder to my computer. So when you install Drive, it'll say, do you want to sync some folders from your Google Drive? You choose the folder that you export your Earth Engine data, and that means I don't need to do anything different. As soon as a new file appears, the Google Drive application will go and download it to the Google Drive folder on my computer. So this is the folder, the file that I downloaded. But even if I don't download, you can see I have my Earth Engine folder. I can just go and download the data from there, because it's always syncing that folder to my computer. So if you say, what's a way to export to my computer? Well, you export to Drive and then sync that Drive folder to a computer, and all your data will be automatically exported. Okay, it's done. So I've loaded this file in QGIS, and you can see it appears different than what I exported. Why is that? Because I exported my raw pixel values And when I loaded in QGIS applied different visualization parameters. It loaded band 1, 2, and 3 versus I want to see an RGB visualization. I can change that and say I want band 3, 4, 3, and 2. And in Earth Engine, I use this 0 to 3000 visualization parameters. So if I apply the same, the image will appear exactly the same as it did in Earth Engine. So again, you have the raw pixel values, you can use them for analysis. If you want to visualize the same way that it appears in Earth Engine, make sure you apply the same band combination and the min-max values that you use in Earth Engine. All right, let's do the exercise.
So for the exercise here, you see the similar script as the previous one. We are having the script where we are filtering Bengaluru from the feature collection, and then we are using that to filter the imagery for the region, and then we are creating median and clipping the image for Bengaluru region. Here you have to do the same thing, change this to your chosen urban location and run the script. So you will have a clipped image for your region, and then you will have to export the image that you have clipped. So you can write the export function. You can use autocomplete option, or you can just go to the script B where we have function to export the image and just change the parameters accordingly. So just do everything, give the region, scale, and image and everything, and try to export the same image that you are clipping here.
I want to share some more tricks for export, specifically the one trick that will help you manage your exports much better. Many times when you are doing your research or do some analysis, you are exporting a lot of images with different settings. Let's say you're trying to find the best model that works for your analysis. And you have many different layers, you're trying different weights, and you're trying different combination of parameters, and you're exporting that. In a typical GIS environment, you will use your file names to describe what you did. So you'll say, composite, parameter 1, this, underscore final, then you'll say underscore final, and whatever, right? You keep kind of playing around with the file names to describe what you did. And then, if you're exporting some 100 images, you don't know what was what. If you're doing this, I'll show you a better trick that will help you manage this workflow much better. Coming to our script that we exported, let's say for this one, I want to export only band 5. So I have this export image, and I'm just selecting the band 5 for exporting. And I want to do this at 100 meter scale. And I want to export it. So if I want to use my file naming convention, I'll say composite underscore band 5 underscore 100 meter, and to describe what I did. Instead of that, what you can do is just before you run the export, click get link. This will take your script, encode it into this URL. So this URL captures the whole script that you wrote. I can take the last part of that script, and now I can say my file name is composite underscore this. And now I'm going to start this task and run this and start. And my export task will run. I'll get a file with this name. Next, I'm trying something different. I want to export band 4 at 200 meter. Just before I run this, I click get link. I'll get another long string of numbers that describes my script. I use that as my file name, and I start this. I don't have to describe what I did at all in my thing. I just have this number that has captured what I did as in my script, and I have the file. So now your export runs. You can see once the export finishes, you can go to your drive and see this file. Let's say you did 100 such things, and you say, now I really like this result, what I found in this file. You have this file and you said, I really like this result. I want to use this. How did I generate this file? Well, I don't have to remember this because I can just take this file and copy the part in the file name, go to Earth Engine, and when I put that in Earth Engine, I get the exact script that was used to create that file. So your file name now describes the entire process of creating the file. If you're doing a lot of exports, if you're doing research, you'll thank me for this. Once you find a file and say, this looks really good, you can now go and recreate the file. This is also great for reproducibility. You did something 6 months back, say, I want to go back to that. Well, you have the file name, which can now generate that file using Earth Engine. So use that in case you're doing a lot of exports. Your file name can describe your outputs. So we are done with our module 1. You are ready to do your first assignment. Let me explain what the assignment is. In your repository, you have a folder called assignments. This folder contains the scripts that describes what you need to do for assignment. After completing module 1, you should have all the necessary skills to complete the assignment 1. The assignment 1 is for you to explore a new data set and create some products and export them. The idea for the assignment is that you are now used to kind of modifying existing scripts and writing 1 or 2 lines of code, but you not built your entire script from scratch. This will give you the skills to say, how do I find some data? How do I visualize it? How do I apply a filter on a completely new data set and generate an output? This will help you build confidence with Earth Engine and practice all the skills we have learned so far. I'm going to work with this data set called verse, nighttime, day-night band. Let me just show you the data set. This is a sensor about the satellite called verse. There's a sensor which collects data at night. Contrary to a lot of the Earth observation satellite, which capture data during day, this sensor is capturing data during nighttime. There are multiple versions of this. We're going to use this one, the stray light corrected version of this. This satellite captures the images over Earth at local time around 1 a.m. at night. So it's showing you what the landscape looked like at nighttime in whatever places it captured the data. This data set is widely used in economics to study, productivity. Nighttime lights closely correlate to GDPs. So you want to know what are the activities. People have found that nighttime lights and GDP are closely correlated. It also shows you the rural versus urban areas. If you want to know which areas are rural, which have less lights, urbanized areas have typically more nighttime lights, and so on. So this data is super helpful to study that. Your assignment is to use this data set and create 2 images, one for May 2015 and another for May 2020 for your city. The result that we expect would look something like this. This is the solution to your assignment 1, where we have created a nighttime lights image for May 2015 and May 2020. Why May 2020? May 2020 was the COVID-19 lockdown in most parts of the world. So what we want to study is what was the change in nighttime lights during COVID lockdown. And if you're in a city which was under lockdown, you should see much reduced nighttime lights compared to the 2015. This is showing city of Bangalore. City of Bangalore has a lot of offices open throughout the night. It's a center for a lot of economic activity at night. During May 2020, a lot of the offices were closed, and you can see this was 2015. And in 2020, you'll see much reduced amount of light. For a lot of cities also, you'll see lights reduce on the downtown areas, and a lot of the lights move to the outskirts because people moved out towards the rural parts where there were no lockdown and so on. So it is useful to study the kind of changes that occurred during COVID lockdown. And this is the output that we want to create. Once you create this, you should also go and export the data as GeoTIFF files, and you'll have those 2 images that you can use to compare the changes in nighttime lights. This is going to be a challenging assignment, but if you do it step by step and if you followed all the scripts, you should be able to build a script that does this.